We're going to put a few more numbers with our friction calculations today. Back on I think it was day 5, I had you working a problem where I told you that a man was trying to push a car, and I told you that the car's mass was 1,500 kilograms, and he was trying to achieve an acceleration of 0.03 meters per second squared to the east. And so you worked that problem that day, and you should have come up with the fact that he needed to exert a force of 45 newtons to the east in order to achieve that acceleration. But the problem was that I told you to ignore friction, and that's something that we really can't do. We really cannot ignore friction in a situation like this. So this kind of calculation isn't going to help us a whole lot because we have to really analyze what else is going on here. So let's assume that this guy can push the car this way, and let's say that he is able to exert, that says the force of the man, let's say that he is able to exert 300 newtons to the east. He is able to push the car that hard. Now, with the calculation that we did, he only needed 45 newtons to be able to push the car, so he should be in good shape, right? Well, no, because what I didn't tell you was that there's a frictional force involved. And I also told you the other day that friction always acts in the direction that is opposite of the motion. It's going to try and slow things down. So the friction, and it doesn't make a whole lot of difference where I draw the arrow, but if I draw it over here, then the force that's due to friction is 290 newtons acting the opposite direction. And so if this is true, what's going to be the net force that he's actually applying? Because he's got to overcome this whole frictional force. In this particular situation, he's only going to apply a net force of 10 newtons to the east, and so he's not going to be able to achieve the acceleration he hoped to, since he would have to have 45 newtons, because that's what we calculated before. Okay, so that friction makes a huge difference in what we're able to do. Now, let's assume, just for the sake of argument, that the guy has a very well-trained dog. And so he ties his dog It's a happy dog, he's wagging his tail. So he ties his dog to the car, and the dog also is pulling this direction. And so the force of the dog, let's say that it's a nice big strong dog, and so the dog is able to apply 150 newtons to the east. And so that ought to help him out substantially, right? Because this force is to the west. So now I have 300 newtons east and 150 newtons east, so that's a total of 450 newtons to the east, but I now have 290 newtons to the west, and so that's going to give me a net force of 160 newtons to the east, because I'm going to subtract those because they're going in opposite directions. So if his dog is helping him, at that point he's going to be able to apply enough force to get the acceleration that he was looking for. In fact, he'll be able to get a higher acceleration because it's higher than what we had calculated that he would need for that particular acceleration. Okay, so this is where these diagrams that we were drawing earlier really start to come in handy, so that we can analyze the forces, and we can analyze what actually needs to happen here. I gave you another document that has a couple of sample problems on it, and so we're going to go through those so I can help you understand how to work some of these a little bit more complicated problems. They're still not too difficult. So in this document, the first problem says, in order to clear an area, a construction worker pushes on a large rock, mass of 300 kilograms, that is in the way. Once he gets the rock moving, it begins to accelerate at 0.12 meters per second squared to the north. If the construction worker is able to apply 400 newtons of force, what is the frictional force between the rock and the ground? Now, you'll notice here that the construction worker has already got it moving, so we're not worried about the static force that the rock possesses because he's already got it going. He's already got it moving, and now we know how much force he's applying as the rock is moving. So if this is my rock that he's trying to move out of the way, and the construction worker is putting a force on the rock this way. So this is the force of the man, and it says that he is able to apply 400 newtons of force. Okay? I know that there has to be some sort of frictional force because there always is. But I don't know what that frictional force is. That's what I'm actually trying to figure out, okay? This force is to the north. I do know that this one is going to be to the south because it's acting in opposition to the motion. So the first thing let's do, let's figure out how much force I need in order to get it to accelerate. I know that the rock is 300 kilograms, and I know that he's accelerating it at 0.12 meters per second squared to the north. So if I use my F equals ma, the mass of the rock is 300 kilograms, and he has it accelerating at 0.12 meters per second squared. And so if I multiply that out, that gives me 36 newtons, okay? So it takes 36 newtons in order to accelerate the rock. He's applying 400 newtons, and so what does that mean this frictional force is? Well, he's applying 400 newtons. If I take off the amount of newtons that it takes to accelerate the rock, then what's left over is going to be what the frictional force is. So that number is going to be 364 newtons. So then I can go back up here and I can say, okay, the frictional force is 364 newtons to the south. Okay? So I have to have a net force to accelerate, and so when I add these two together, that's going to give me that net force to accelerate. I can calculate that net force by using my F equals ma. Right? So let me make a little bit more space here, and then we'll go through this second problem. All right, second problem says a man needs to push a desk across the floor. Mass is 100 kilograms. The static frictional force can resist motion with as much as 196 newtons of force, while the sliding frictional force is only 110 newtons. How much force is necessary to get the desk moving? Okay, so let's stop there for a second. I have a desk and the man is trying to get it moving. Well, which frictional force is it that tells you what is needed to get an object moving? Is it the static or is it the sliding? Well, hopefully you said static, because static is what the frictional force is that keeps an object from getting started to move. So in order to get the desk moving in the first place, he has to apply 196 newtons. Actually, he has to apply just a little bit more than 196 newtons in order to get it moving. So that's the answer to the first question that's on there. He has to apply a little more than 196 newtons in order to get it moving. Okay? Then the second part of the question says, if the desk accelerates at 1 meter per second squared to the west when the force is applied, how much force did the man use? Okay, so it's always a good idea to draw a picture. So let's say that here's the desk, and I know that the man is pushing on it this way. So here's the force of the man, and I know that the force of sliding friction is going to be opposing it. Okay, do I know the force of sliding friction? I do, actually. It's actually 110 newtons. Okay, I also know that the desk is accelerating. So if I use F equals ma, then the mass of the desk is 100 kilograms. and the acceleration of the desk was 1 meter per second squared. So that math's pretty easy. 100 times 1 is just 100. So it takes me 100 newtons to achieve the if I could spell, the acceleration of the desk. Okay? So 110 newtons is opposing it. It takes 100 newtons in order to overcome the friction. So if I have 100 newtons to accelerate, and then I have to apply 110 newtons to overcome the friction, that's going to give me a total of 210 newtons that the man has to apply. So the force of the man is going to be 210 newtons to the west. Okay? So when you're working these problems, just to try to summarize here, you have to apply enough force so that you can both overcome the sliding friction and so that you can accelerate the object. So the force of the sliding friction plus the force that you need to accelerate is going to give you the force that you have to apply. Okay? So on this problem, we knew the force of sliding friction and we could figure out how much we needed to accelerate to find the total force. In the previous problem with the construction worker and the rock, we knew the force of the man and we knew how much force it would take to accelerate it. So there we had to subtract it to get what the sliding friction was. Okay, so that's going to be the general rule. You're going to take the force to overcome friction plus the force to accelerate, and that's going to give you the total amount of force that you need to apply to get the thing moving and accelerating at the same time.